So yesterday we got into the features of velocity time graphs. They could show us trends on motion of a moving object like position time graphs, but they have their own features. So we got to be careful. Like we said yesterday, like we knew from the past that a flat line on a PT graph meant stop, but a flat line in most places of a VT graph doesn't mean that. So we just got to keep them straight. And like I already reminded you, we won't be running into curves on velocity time graphs, or at least be responsible to do any math with them, because that gets like a little calculus related. But anyways, so these are like the questions we had on the study guide last week, but just different kind of graph. So some of these are more specific than others. So if you got it wrong though, and don't have something along the lines of what I draw, just fix it before you turn it in. At the end, we should be done with this today, and you can upload it to Classroom. You get a few points. All right, so line A in the first one says moving at constant speed in the negative direction. What kind of line am I going to draw on a VT graph for constant speed, negative direction? What kind of line does it have to be? Constant speed on a VT graph. What did we say yesterday? It is straight, but be more specific. Not just straight, but is it sloped or flat? Flat. And it would have to be, since negative direction, all negative velocities are down in this quadrant, right? So anything down here in this quadrant that was flat would satisfy moving constant negative direction. Make sense? And then the other one would be, it's also constant, so it would also have to be flat. It would just have to be up here in the positive V's. That quadrant's all positive, right? Anything like that will do. All right, the next two boxes say the word speeding up and slowing down, and the couple boxes after that basically mean that in the way we've learned before in the past. Oh, one thing just looking at it now, I totally forgot to tell you guys. The final box in the bottom right, I don't like the directions. I think there's something unclear about it. So just cross out that box. Even if you did put something in it, there's an issue with that one. So I don't want to confuse you guys. So we're just going to skip it, okay? All right, so let's go back to this one up here in the top right. Moving in the positive direction and speeding up. All right, so remember, these flat lines represent constant velocity. So these lines have to be sloped somehow. If we're speeding up in the positive direction, how should line A kind of look? Go. Very good. That's the main feature of speeding up, getting further away from zero. Now, there's two ways we could get further away from zero. Up, away, or down, away. Since it said moving in the positive direction, it should be which one of those? Up and away, right? So something that looks like this, getting away from zero, but staying in the positives because of that, would be line A. And now that it has a non-zero slope, we don't have to do this yet. On the back side we do. But we should hopefully remember that if we would take the slope of this, do the change in y over change in x, then that would give us our exact value of acceleration if we had numbers. And it would be non-zero, positive slope, positive acceleration. All right, then speed, the other option then, that I kind of already said, was we could speed up the other way in the negative direction as well, right? So still going away from zero, speeding up, right? But all these are in the negatives down in this quadrant. But this particular box shows us what we keep saying. Don't forget that this is definitely a positive slope and this is a negative slope, right? So what that really means is this is a positive acceleration, this is a negative acceleration. And this proves the fact that we've been saying all along, that just because the acceleration is positive or negative, that doesn't guarantee me if I'm speeding up or slowing down. It's all depends on what kind of velocities I'm in to begin with, plus or minus, because both of those lines could represent speeding up, which they do, right? So then on the flip side of that, this box is slowing down. Very similar, but now instead of going away from zero, when you slow down, you go towards zero, right? So in this one, we should have sloped lines going towards zero. Line A says moving positive, so that would have to be up here, positive velocities. going towards 0. And the opposite of that, still slowing down, but the opposite direction would be going this way, and slowing down, moving in the negative direction for line B. We all good with that? All right, and the next two boxes are really just these same two again, but just like on the last study guide for position time graphs, sometimes they don't use the words speeding up and slowing down. They use the fact that you know the signs of the velocity and the sign of the acceleration. Just keep remembering, if the signs are opposite, like in line A over on this one, if the V is positive and A is negative, does that mean speeding up or slowing down if they're opposite signs? Who remembers? This is the first time we went over this. It doesn't say the word speeding up or slowing down anymore, does it? So we should be able to tell by the signs. If the signs are opposite that they give for V and A, is that speeding up or slowing down? Slowing down. So this is really saying moving positive and slowing down is another way to think of what that's saying, which we already did that one. They're just saying it in a different way. So to be moving positive and slowing down, this line A is going to look exactly like the line A from over here, which said that, right? And line B, this one says moving positive and positive acceleration, moving positive V and plus A. Plus plus, or two of the same signs, mean not slowing down, but speeding up, if you guys remember. So speeding up in the positive direction, which, like I said, we did already, and up here, that would be the same thing as line A and the one above it. Positive speeding up, plus plus. So this one would be, this one, line B, they're both up there. Notice the fact, though, they're both in this quadrant because they both had a positive velocity, and that's where the positive velocities are, right? So let's move on down to this next one. Same idea, different signs. Different starting directions. Negative, negative, again, means what? Same sign, same sign. Speeding up, slowing down. Same sign, same sign. Speeding up, this time speeding up in an original negative velocity direction. So that would be the same thing as that one. And then negative, positive for line B. Slowing down, but in the negative direction. So it would have to be down here. That would be the line that just flips and goes like that. So just different ways to ask what this box and this box asks. Any questions on that? All right, before we go on to number 3, which should be easy because we did some of those yesterday as well. I'm going to don't have to write this down, just pay attention. We learned last week with PT graphs. I probably quickly mentioned this yesterday, but I'm going to go over it more thoroughly right now. Turning around on the old style graph, there'd be a full parabola, right? Like that. Or possibly even like that. Those are the two possible parabolas, right? Now, I told you VT graphs aren't going to curve, right? If that's how a PT graph represents changing direction, does anybody remember or know what a VT graph would do to represent changing direction? Big hint, these are all positive velocities up here, and these are all negative down here. For a VT graph to change direction, it can't curve. I said we're not going to have curves on it, but it can still represent changing direction. Any ideas? Yeah. Good guess, but no. That's an often common guess. I see why you say that, but no. I'll show you why once we get the right answer. Any other guesses? All right. Remember, negative velocities mean you're going in a negative direction. Positive velocities, positive direction, right? If I did something like this, wouldn't that represent changing direction? Because didn't my line go from negatives over to positive velocities? So simply crossing the x-axis means a change in direction. Or in other words, this black line here represents basically what this blue line did here. All right? This one shows me from old stuff that I'm going in a negative direction to begin with because it's going downward. All right? On a PT graph, the direction is based on where you're going, sweeping down or sweeping up. So I'm going in the negative direction, and it's flattening out, so it's slowing down, right? You can think of it as there's two halves to these parabolas, right? A half where it's slowing down in the negatives, and isn't that what this one's doing down here? This is 0 right here, right? Slowing down, and we're in the negatives because we're down here, right? But then, right at that moment, before you change direction, before you completely reverse direction, for a brief moment, you've got to do what? Stop. And isn't that what's happening here? The moment I cross, for a brief moment in time, I'm at zero velocity, right? That stop is shown on a parabola by being flat for just a moment, right? Right there. And then it crosses over and starts going positive because it's sweeping up. These all are going positive now too, right? This one's sweeping up and getting steeper. This one's getting further away from zero. That's how they both show like the same idea in their own unique ways. And not to talk about it too much more, but I could go this way too, right? That green line on this one would represent this, the accompanying line that would go along with this one, just in the off flip directions. All right. So main point is on a PT graph, when you turn around, it makes a full parabola. On a VT graph to turn around, it's going to go through the x-axis and pass from negatives to positive or positive to negative. All right. Going back to over here. Oops. All right, so all we had to do here is just remember how to find slope, and remember the slope is your acceleration. So we do what we always do. I'll just show the work colors. There's a little bit of room, it looks like above. So we're always trying to pick a nice point. I would say a nice point here would be here at the beginning and here, right? And just to look closely on that. The very beginning point looks like that goes by twos if you look closely. 2, 4, 6, 8, 10, right? So we're at 0 x coordinate for the time at t equals 0. And the y coordinate, which represents velocity, looks like we're at 4, right? So that point right there is 0, 4. The point over here it ends on looks like 8 and about 32 for the y. So we just need to do the change in y over the change in x. So that would be 32 minus 4. And remember, if you need to, if it helps, you could write over this point x1, y1, right? And over this point x2, y2. And hopefully remember that y2 minus y1 is 32 minus 4, and x divided by x2 over x1, which is 8 minus 0. So 32 minus 4 is going to be 28, right? 28 over 8. That's not a nice number, is it? All right, so we're going to put it in decimal form. That's okay if you don't have a calculator handy. I'll just do it for us. 28 over 8 divides to a decimal of 3.5. Now, this does represent the acceleration since this is a VT graph. What's the units on acceleration, guys? Not meters per second, but almost. Meters per second what? Squared. And you could see it's positive through the calculation, but you could also see through the visual it's definitely positive because it's going uphill, right? Make sense? Basically just doing the same thing with the second one. So this point down here looks like 12-second marks at 8 meters per second. This point over here looks like 0 is 0 for the time, and 32 here is definitely going to come out a negative number because it's downhill, right? So again, if it helps you, x1, y1, label them, x2, y2. So we'll do 8 minus 32. 8 minus 32. Divided by x2 minus x1, that's 12 minus 0. So 8 minus 32 is going to be 24, negative 24. 12 minus 0 is 12. This one's going to equal negative 2. I'm running out of room here. Meters per second squared. As long as you find basic slope, the most important thing is what that represents. Is that it represents acceleration. Don't forget, don't get it confused. If we were finding slope on a position time graph, it wouldn't represent acceleration. We'd find slope the same way, but it would represent what? On a position time graph, it's the what? Not the acceleration. It's, anyone remember? Not quite. We can read displacement straight from it, but for the slope of it, it's the velocity. All right. So the slope of the PT graph is velocity. The slope of a velocity time graph is acceleration. And there is a such thing as acceleration time graphs, but typically in early physics, like intro physics, we don't study acceleration time graphs mostly for reasons due to calculus and what we're limited to. Okay. But finding slope is just algebra, and we could do that. All right, I'm going to skip for now. If there's time, we'll come back. If we run out of time, I'll probably skip the middle part totally. Okay? So skip not all of number 4. Don't worry about that. It has this thing to do with area. Let's go down to the last part. Actually, I didn't erase one of these from before. Okay, here's the deal on these ones. Next week, you're going to have some more concept builders. Like we did earlier this week, we did them on PT graphs. We're going to do VT ones. And one of the concept builders in particular will have you do something like these questions, where you have to, if you're given information from a PT graph, draw the corresponding VT or vice versa. I think that's Tuesday. We'll work on some of those in here. But anyway, they give us a position time graph. This one only has one true segment, but actually it looks like there's a little flat line there to begin with. But what do we know from a curve like this on a PT graph? Tell me everything you could remember. If I see this is a position time graph, last week's kind. It's curving. Notice that curve's getting steeper. What does that mean? It is accelerating, exactly. What kind of acceleration? Speeding up or slowing down? Speeding up. You're right. Why? Why did you know that? Basically, yeah, it would, because of the way it's curving, it's getting steeper, right? If it gets steeper as time goes on, it's getting faster. And since it's going upward, it's going in the positive direction, right? So we need to make the corresponding VT graph. We need to make a VT graph that is speeding up and going in the positive direction. So if we do that correctly, oh, and by the way, it should also start from 0. Here's why. This is a subtle feature of this graph. Look at the very beginning. Doesn't the very beginning, first moment of this graph, have a flat line? Remember, a flat line on a PT graph means you're what? At rest. So we started at rest, didn't we? So that means my VT graph better start at rest or 0, right? And since it has to speed up in the positive direction, basically what we're saying is that graph and that graph mean the same thing. They're just two different styles of graph. Those two are telling me the exact same information, just in two different styles of graph. Make sense? Now this graph over here has 2 segments, so let's worry about one segment at a time. If this one has 2 segments, our new one will have 2 segments. So look at this curve. We just said a curve represents acceleration, but what kind of acceleration is this curve? Is this curve speeding up or slowing down on this one? Slowing down, right, because it's flattening, right? So is it slowing down in the negative direction or the positive? Sweeping downward, so it would be the negative direction. So we need to start by having a segment that is slowing down, but in the negative direction the whole time. So that would, negative direction on this graph means being in this quadrant with negative velocity. Slowing down means going towards 0. So that segment goes to here. I'll go a little bit past it. Shouldn't go past. Something like that. Make sense? So that first segment of that curve and this first segment of this mean the same thing. But this one eventually comes to a total what? Total stop. So how do we say staying at total stop on this one? Just flat at 0. Staying at 0 velocity, right? Does that make sense to everybody? So you'll have a concept builder that throws more of these out at you, but you'll be doing them in class. So if you struggle on any of them, please ask, okay? Don't sit there when I assign those concept builders and be lost. I'm here for help so you guys can finish them. All right. There's probably not quite enough time to even bother getting started on this next segment. I'll just tell you a quick thing about it, but we're not going to do it. There is another thing that you could tell from a VT graph if you take the area, what we call the area under the curve. And it would actually give you the displacement. In all honesty, there's no lab where we're going to need that. So because of that, I'm not going to really worry about going over it. So we're not going to do, none of our concept builders are going to ask you about area. Not that it's not important, it's just that you're never going to run into it with any other application we have, so might as well not do that part. All right, so I just want you now, as long as you finished what we did together, I want you to upload that right now to the assignment that you found it in. So you get a couple points for completing it. And you could, next week I'll remind you when we're doing the concept builders on Tuesday that you may use these and have these out in front of you to help. make sure you upload that. I'm going to tell you a few other things about next week, since I'm not going to be here tomorrow.